right. Sharing my screen, recording. Nice. We are in the home stretch. Boop, boop. I know I can just tell there's a general burnt out vibe on campus. And yeah, there's just no way around that. But also we as a class are into kind of the fun stuff of the course, or at least how I think of it. I like to end with regression just because it's a nice, easy, high note to end on. All right. I shouldn't say easy, but predictable. But because we use regression lines to make predictions. I know. Feels like with your jokes landing with Joe. All right. But that doesn't mean I'll stop trying. Here we go. Just as a little bit of review, right? We got an X and a Y axis, and we were talking about scatter plots. We kind of got the boring stuff of regression out of the way. Regression is fitting a line of best fit. And so we kind of got, in my opinion, the boring stuff out of the way, residual plots, and just kind of the general theory behind scatter plots or regression. This won't print there. And so in general, we said, well, we're going to have the response variable on the y-axis and the explanatory variable on the x-axis. Now, all we got to last day was if I fit a line, the general equation of a line, remember, is y equals, usually in high school, they teach mx plus b for some reason. Could be any variables, but those are the ones they've chosen. So usually that's what people are familiar with. Whatever's attached to the x is a slope, and whatever is on its own is the y-intercept. That's all we're gonna review from last day because it's really all we truly need. Okay. Today we're going to calculate what the slope is, calculate what the intercept is, and then on Thursday I'll show you some R output so that you know how to deal with that as well. Okay. And so just kind of multiple ways that we can find the slope and the intercept. One thing, the reason I bring this up, right, the x and the y-axis, the response and the explanatory variable, is because it's going to be so important that we keep track of which is the x and which is our y, because in our formulas, you're going to have the standard deviation of y and the standard deviation of x. And if you mix those up, it'll make a real mess. Okay, so that's why that's important. But today, section 8.2 is just called least squares regression. We like to use the term modeling. Okay, so this line models this relationship, or any time that you try to, I guess, model describe the relationship. How can I say it without using the word model? Right, when we're trying to kind of summarize a relationship, we're modeling that relationship. And so just like before, when we used a sample mean to learn about the population mean, for example, now we're going to have a sample line of best fit, but it is really trying to estimate what the population line of best fit looks like. So I'm just going to introduce that notation here, and we're not going to do a ton with it or anything at all probably, but it's good to know that there is that link still. So we want to model the population relationship between x and y. So the population relationship between X and Y. Okay. What that looks like is you've got Y is beta naught plus beta 1 X. And then I'm gonna do it in kind of a dotted line because I don't want you to think too much of it, but there is an error term on there, which is the noise that the X, so this line doesn't capture. It's technically there, you're good to ignore it, it's totally fine, but I just, if you see it elsewhere, then it's the noise. Okay. So, right, this line can only do so much, and then there are other factors at play, and that would be part of that error term. Okay. Now, in terms of beta naught, that's going to be the population y-intercept. And beta 1 is the population slope. We're not going to know what those are, right? But we can estimate them using a sample. So using a sample, we can estimate beta naught and beta 1. And for our estimates, we can get y hat. I'm kind of blanking on if there should be a hat on this, the population one. I think so, but I think we're safe without it. But in terms of our sample, we've got our y hat, which remember is the predicted value of y. We've seen hats before, but not in this context. So the context will tell you if it's a regression predicted value or if it's a sample proportion. Never the two shall meet. To estimate beta naught, we use a B naught. And to estimate beta 1, we use a B1 times X. Remembering that, I'll just make a note here, the y hat is the predicted value of y. B naught is the sample y-intercept. And B1 is the sample slope. Those are the values that we're going to learn about. I'd say the kind of smoothest way to learn about the slope and the intercept is to introduce the formulas, and then we'll work with these formulas. But in terms of the math, it's really pretty manageable stuff. Oh. Here. And you'll have these formulas on the formula sheet as well. Speaking of formula sheets, I'll post an assignment for you to work through today. Okay. To identify the least squares line from summary statistics, so that means that we're going to have to be given this information, which I will give you, right? Even if you don't, right, remembering that from your scatter plot, you're going to have a column of X's and a column of Y's, right? And that many observations. And so from each column, you could find this, the standard deviation, you could find the mean, right? And so you're going to have a standard deviation of X, a standard deviation of Y, the mean of X, the mean of Y, right? These all depend on assigning the X's and the Y's appropriately, right? To estimate the slope parameter, B1, we're going to use the standard deviation of y divided by the standard deviation of x times the correlation. So here, this is where it's really important that you don't muck up your x's and your y's, right? 1/2 is way different from 2/1, right? So you're going to have very different results if you switch them accidentally.
What's the big R?
That's the correlation. I can't seem to shake it. R is little r, which is the correlation. I use little r. I get why they want to use big R. I get it. I can't. Notice the standard deviations are both measures of spread. They have to be positive, right? You can't have a negative spread. So those values are both positive. So that fraction is positive. So the only way that we can get a negative slope, which makes sense if I have a negative relationship, that's going to come from the correlation, right? And so that's why you need that correlation. Correlation, we said last day, is a numerical measure of the strength and the direction of a linear relationship. We don't need to think about how we get to the next part for the intercept, but it is kind of fun to know that the point x bar, y bar is always going to be on the line, just because of how we found things, right? How we find this line. X bar is the mean of x, y bar is the mean of y. So at some point, you're going to have the averages coinciding, and that point is always on the line, just as a fact. So from there, blah, 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 point slope form, we get that the intercept, we can find the equation of the intercept using y bar, which is the mean of the y's, minus the slope, which you just found. So that means that you have to find the slope before you can find the intercept, right? But then times the x bar, which is the mean of the x's. Right? So just to kind of show you what it would look like on the formula sheet, let me just make myself some room here. I would give you that y hat is b0 plus b1x, where B1, and I list them in the order that you would calculate them. B1 is SY divided by SX times R is the slope. And B0, just to summarize what's above here, is y bar minus b1 x bar is the y-intercept. Pretty quick here, I'm going to stop calling it the y-intercept and just call it the intercept. The x-intercept is not useful to us. It's where the predicted value would be 0. And maybe that is interesting, but not, not typically. So to calculate these values, we need 5 things, right? We need the standard deviations of x and y. We need the correlation. And then I need the mean of y and the mean of x, right? So 5 things. So I'm going to list those here. So to calculate B1 and B0, B0, we will need S subscript y, which is the standard deviation of y. Sx, which is the standard deviation of x. Big R, little r, they mean the same thing. They're both the correlation. we need y bar, which is the mean of y, and x bar, which is the mean of x. We're going to run through the example that they have in the textbook, which is on, I think they call it gift aid at a college or at a university. And so, but before we do that, let's talk about the interpretation of the slope and the intercept, because that's one of the things that I'm going to ask you, right? Calculate the slope, calculate the intercept, interpret the slope, interpret the intercept, right? And so, like I said, these questions are, pun intended, very predictable, right? They're kind of a set procedure of the questions. So once you've got them down, then you know what you're doing. Okay, so to interpret the slope and the intercept, all we really do is we apply the definitions to this context. Right? So to interpret the slope and the intercept, we apply the definitions of the slope and the intercept. Of the slope and the intercept. So it really helps to remember that the equation of this line that we're interpreting now is y hat is b0 plus b1 x. So in terms of the slope, and I'll put a little line under it for it being a definition. The slope is your b1, right? So in terms of the definition, the slope says that for each unit increase in x, right? So as x goes from 1 to 2, 2 to 3, 3 to 4, right? We expect to see a slope unit increase in the predicted value of y. Right? So you can, with a little bit of practice, you can extract the definition from just this line here. So the slope for each unit increase in x, and of course you would replace that with whatever the question is about, right? Whatever x is in the question. So for each unit increase in x, we expect to see a slope, and that's where you would replace that slope with that b1 increase. I'll say b1 increase, and maybe I'll throw in unit increase in the predicted value of y. I say increase because it's the safest option, right? Even if I say a -4 increase, you think, oh, that's a weird way of saying it. Why wouldn't you just say a 4 decrease? That's fine. That's technically correct, right? But a -4 increase is also safe, right? It doesn't really make sense. But if you said a -4 decrease, right? If you forgot to drop the negative, then what you're saying, it doesn't make sense. Technically, that's an increase, right? A 4 unit increase. And so that doesn't, it doesn't work. So just to kind of save me from myself, I just always say the slope, even if it's positive or negative, increase. It sounds weird. And maybe once I'm comfortable and I can kind of make sure that I've dropped the negative, if I'm saying decrease, for example, then this is still safe. Okay. So even if the slope is negative, we can still say increase. Wait, didn't mean to hit that. Right, so for example, if I have a -4 increase versus a 4 decrease, which means you have to drop the negative. So then you would swap out whatever x is, we expect to see whatever the slope is, and then replace the y with something question specific, right? Your x's and your y's and your slope that you found. Yeah. But that's the general definition of a slope. Now, the intercept, we can also look at that equation, least squares regression line. The intercept, B0, okay, is the predicted value of y when x is 0. Right? So we know that that's the intercept, but we have to kind of apply the definition, right? And so the intercept is the predicted value of y when x is 0. And again, right, you would replace your x's and your y's. And I guess you would say something like the predicted value of y is the intercept. Yeah, sure, let's do that. Instead of just rewriting it. The predicted value of y is the intercept B0 when x is 0. There. Often I have a follow-up question about the intercept and I ask, is it meaningful, right? Is it useful to know what the predicted value of y is when x is 0? And this is where there's no wrong answer. There's not necessarily a right answer either, right? What you have to argue is, do I care about x being 0, right? So you'd have to argue it one way or another. Yes, it is meaningful because it is important to know, for example, what the square footage, if the square footage of a home is 0, what the predicted price would be of that home. I personally, I would say, no, that's not important to me. I don't care about that. That home clearly doesn't exist, right? And so my argument would be, no, that's not meaningful because this house doesn't exist. But if you can find a way to make that meaningful, then that's fine. But your argument is going to be about x being 0. So there's no wrong answers unless you say, is it meaningful? Yes. That doesn't mean anything to me, right? 0 marks. Is it meaningful? No. 0 marks. You have to revolve your argument around x being 0. Okay, so often I'll say something like, is the intercept meaningful? This is where you argue whether the predicted value of y when x is 0 is meaningful to you. So argue whether the predicted value of y when x is 0 is meaningful to you.
So for your example, could we argue x at 0 is meaningful because it gives you the value of land?
So whatever you argue, just back it up with x is 0, right? Do I care about that? Yes or no? Right? And so, yeah, lots of ways that you could argue it. Okay? One thing that I do is often you'll have a scatter plot. So if x equals 0 is within a kind of a reasonable range of that scatter plot, then it's usually meaningful, right? Then it can happen, it does exist, right? So then maybe it's a nice kind of jumping off point, but I'll show you with an example. Da 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 da. Aren't you guys so glad we did residual plots last day? All right, so the example that we're going to talk about is family income and gift aid data from a random sample of 50 students in the freshman, I guess it's singular, freshman class. I don't know, I'm not American. Of Elmhurst College in Illinois. Okay, so gift aid is financial aid that does not need to be paid back as opposed to a loan. And so we're looking at this scatter plot. And first thing I would probably ask you to do is to describe the relationship here. So let's start there. Looking at this scatter plot, I've got the gift aid from the university and then the family income on the x-axis. And so if I had to describe this relationship, I would say it's a moderately strong, right? I see a pattern. It's not crazy strong around this line of best fit, but a moderately strong negative linear relationship, right? Three things we touch on, right? The strength, the direction, and the linearity, right? Does a line make sense here? In this case, I say yes. So we will. They did a weird thing where I think this dotted line is fitting it by eye, which is kind of like eyeballing it. So please ignore that and only look at the solid line. Right.
Use that in my career
Just
eyeball the plot.
Yeah, you'll make the big bucks that way. Yeah. Yeah. So what's this equation? Oh, I don't know. No clue. No clue. Yeah, they love that. When you try it, let me know how it goes. Yeah, so I don't know what that was all about, but just look at the solid line, which is the least squares regression line. So I think I touched on it last day. We definitely talked about the conditions for fitting a least squares regression line, right? First thing, it has to be a linear relationship before I fit a line. That feels obvious, right? The residuals have to be normally distributed, right? I have to have constant variance, so kind of even spread around this line, right? And in this case, I would say that I do. And then the last point that I probably glossed over is that all these points have to be independent of each other. That's not really a surprise. We've had to talk about independence this whole class or this whole course. And the fact that it was a random sample tells me that, okay, now I can assume that all these 50 students are independent of each other. There are scenarios where the x's, right, if you're going day by day by day, if you're looking at weather, for example, right, then the x's often, if they're in time, right, then you're talking about a time series, which I would argue is its own course, right? Talking about time series analysis, because then you can't assume that independence anymore, right? And so you need to kind of work around that. But for us, we're just going to assume that we're not talking about time. And even if we are, we still apply these same methods. So just as a reminder, right, x-axis, y-axis. If I have the scatter plot, right, then I am being told which is my x and which is my y, right? So it might be a good idea to just kind of jot that down, right? Y is the gift aid, let's call it, and X is the family income. Mostly as a reminder to myself later on. We're given the summary information, which is what you will have as well. Bring that in here. Right, we said we needed 5 things. We needed the means of X and Y, we need the standard deviations of X and Y, and then we need the correlation. Right? They've been generous with the information that they've given us here, right? They've told us that, hey, family income is X. And then they've labeled it X bar SX, right? Y bar SY, gift aid is the Y. I would expect you to be able to handle it even if these guys weren't explicitly mentioned, right? That's the kind of scenario where you need to say, okay, Y is the gift aid, so then this would be my Y's, right? The mean of Y, the standard deviation of Y. Family income is my X, so this is the mean of X, the standard deviation of X. Right, so even if these aren't given, right, you need to be able to handle that. But here they're being super nice, which I am not, I guess. I'm giving it to you. Okay. We're going to run through this example just as how I would expect a question to go on the final exam, right? And so part A, I would probably get you to describe the relationship, but let's get straight to find the slope. Find the slope. All right. We've got the equation B1 is SY over SX times the correlation. The standard deviation of the Y's is 5,460. Sometimes we do weird things like, because this is money, we might have, let's say, divided our data by thousands or something like that. But here I'm just going to keep the scale in dollars. 5,460 divided by the standard deviation of X, which is 63,200. You can see how if you reverse these, that would make a real mess, right? And so these values, if you reverse them, would be drastically different. The correlation is negative 0.499, which just reinforces my statement about kind of moderately strong negative relationship, right? 0.499 is kind of right on the cusp of that vague cutoff that I had where it goes from weak to strong, right? Just as a guide. And then negative, of course, means that it's a negative relationship. So I get negative 0.043109811013. The question, of course, will tell you to use the rounded values or to keep and store all these values, right? So you'll follow instructions. I'm going to keep all these values because I want it to match the R output later as closely as possible. Or software output, I should say. But it is R. Find the slope, done. Find the intercept, can do. From the formula sheet, you'll grab B0 is Y bar minus B1 X bar. The mean of the Y's was 19,940. Minus the slope, which we just found. So this is where I would keep it in my calculator or kind of store that value. Negative 0.043109811013 times the mean of X, which is 101,780. Remembering bed mass, right? You're going to multiply these before you subtract that value from 19,940, right? Kind of the most common mistake I see here is dealing with these two and then multiplying, which is also going to make a mess, right? Or forgetting the negative here, right? Subtracting a negative is the same as adding, so that would also make a mess. Algebraic nightmares. 19,940 minus, and once I've multiplied that out, negative 4,387.716475. And I write it like that to emphasize that I've multiplied those two together, which lands me at an intercept of 24,327.71647. We got the slope, we got the intercept. Now a natural follow-up might be, what is the equation of the least squares regression line? What is the equation of the least squares regression line? On your formula sheet, you will have y hat is b0 plus b1x. Now we just plug in the values that we found, right? And just for later, it might be nice to write out y is the gift aid. Put a hat all over that. The predicted gift aid is B0, which is 24,327.71647 plus the slope, but the slope is negative, so I'm going to make it negative, so minus 0.04311, rounding a little bit, times the family income. And I'm going to just bump this over. So far, so good, I think. All right. Part C, done and dusted. I guess they're only parts in my head, but they're all the parts that you'll see. Part D, interpret the slope. Right. This is where we take the definition of the slope and apply it to this scenario. Interpret the slope. The slope, remember, says that for each unit increase in X, I expect to see a slope increase or a slope unit increase in the predicted value of Y. So for each unit increase, right, which if we want to be specific, $1 increase is a unit increase in family income, right, in X. So in family income, we expect a negative 0.04311 unit increase, and this is where I'm going to just stick to my guns and say negative increase. That's totally fine. Unit increase, right? Or 0.04311 unit decrease, and that's fine too, in the predicted value, or in the predicted gift aid, but maybe I'll say the predicted value of the gift aid. No, let's just stick to the definition, right? Predicted value of Y, the predicted gift aid. You don't look sold.
After the 0.0431 unit increase, would it also be dollar increase? Or could it be?
Yes. How about that? Yeah. Good. In the predicted gift aid. Good. How about part E? Interpret the intercept. And then the follow-up is it meaningful? I feel like you guys could make up these questions with what I just introduced. Oh, what could we ask? Well, let me guess. Interpret the intercept. Is it meaningful? Okay. The intercept, right, is the predicted value of Y when X is 0, right? Or kind of some take on that. I think I altered it slightly from what I usually do. The predicted value of Y is the intercept when X is 0. Okay. So the predicted gift aid is the intercept, which is 24,327 and 72 pennies, is 24,327.72. So the predicted value of Y is the intercept when X, which is the family income, is 0. When the family income is 0. That's the interpretation of the intercept. Is it meaningful? I could be convinced either or, right? Can you have a family income of 0? Yes, right? Arguably, there would be some sort of assistance, so then you would have, you need money, right? But so where is it coming from, right? You could argue it either or. So then my go-to move is to look at the scatter plot, right? And so I have the scatter plot here. And when I look at my x's, right, and I let x be 0, it looks like that can happen, right? Or at least very, very, very close to it. So it's not that far off, right? So then it is meaningful to me to know what the predicted gift date is when the family income is 0, right? Because that's kind of the starting point, 24,000-ish. You can also look to make sure that your values kind of make sense with your graph, knowing that, okay, at x equals 0, right, it's around 24, looks reasonable, right? So you're just looking for reasonable values, not exact values. So is it meaningful? I'm gonna use the scatter plot to back my statement up. So since there are data points and maybe since there are data points at or close to x equals 0 in our scatter plot, x equals 0 in our scatter plot, the intercept is meaningful. And I'll kind of boost that with, since it can happen that the family income is 0. Right, so if you talked about the family income being 0, does that make sense? Does that not make sense? Right, then you're good. There's no wrong answer there. Okay. Before we can do these follow-up parts that are in my head, we need to introduce a couple more things. So when we're talking about, okay, is the intercept, is it within the range of our data? If it was not, right? So if the scatter plot looked like this, that this was at 50,000 and then 100,000. So if we just bumped all these over and 0 wasn't within the range of our data, that would be an extrapolation. Now, extrapolation is when we use this line to predict values outside the range of our data. So kind of the same problem that we've seen before is, okay, well, we've used this sample information. So just these values of x, okay, have built this line, right? So even though lines as a fact go from negative infinity to positive infinity, right? You could put in any value of x here and get a predicted value of y, right? But it's only reliable within this range of the x's, right? So when we're extrapolating beyond the range of our data, then all our predictions, although they might be our best predictions, are unreliable, right? When we're predicting values inside the range of the data, it's called interpolating, and that's a good thing. But then when we're extrapolating, that's bad. And I know the author of the textbook, she loves to say treacherous. Extrapolation is treacherous. I think she says treacherous like 3 times in the textbook or something, which is a lot more than usual, I think.
Control F to do that. Did you?
No, I've probably read the textbook like 5 times. So every time I see it, it's jarring to me. Treacherous. Yeah, I know that thing inside and out. So it's like, you can too, but yeah, how many times are you searching it right now? I can tell. Got that hunting look in your eyes. Yeah, I am curious too. All right, so extrapolation, the definition is when we use our regression line, okay, to predict values outside the range of our x's in our data. So extrapolation is when we use the regression line. Yeah, I'm so curious now. To predict values outside the range of our x's in our data.
You were very close.
Oof, feels good.
4.
Oh,
The 1 is a title.
well, so I was gonna clarify, do the headlines matter? Do they count?
Well, then you'd be right.
And that's gotta feel good. I get that green check mark. Yes. You know what? That's good to know. I hadn't actually counted, so I can't take too much credit. But it's good. How do I? I want to keep it on this line here. Okay. So I've got this the scatter plot. It's the same one that we've had before. So here, the range of our x's. And if you're from a mathematical background, saying the range of x is probably a little bit, right, gut punchy, because the range is usually for our y's, right? But I just mean it in the sense of, okay, so from the minimum to the maximum of our x's. And so here, the range of x is roughly from $0 to roughly 300,000. So sometimes, or quite often actually, the intercept is an extrapolation, and that would mean that it's not meaningful, right? It just is where it crosses the y-axis. But just kind of bolster this line, right, goes from negative infinity to positive infinity. So we can make predictions. Okay. So straight lines, just as a fact, straight lines go from negative infinity to positive infinity. But predictions are only reliable within the range of our data, right, that we built this line from. But predictions are only reliable within the X range of our data. And this we can interpolation. Yes?
Does the do predictions get less reliable the further you go away from the data?
Yes. So you can kind of push it a little bit,
Yeah.
right? Is it reasonable to think that 300,000, an income of 300,000 going to 350 is still probably safe, right? But at some point, if you go to a family income of $1 million, let's say, then you would likely get a negative gift aid prediction, which at some point you just hit zero. You're not going to have a negative gift aid, although maybe in a roundabout way it is, because then if if your family's making $1 million, they're probably donating. But anyways, let's not read into it too much, right? That would be a negative gift aid in a roundabout way, but it doesn't work like that, right? So at some point you just hit 0 and then that's it, right? And so a really common extrapolation example is if you're trying to predict the height of a child, right, based off of their age, then between the ages of 2 and 10, let's say, it's a very strong linear relationship, right? We just keep growing and growing and growing and growing. It's only because of our knowledge of kind of human growth, right, that we know I can't use that line to predict the height of someone who's 40 years old, right? So we have that mental stopper, but that's not always going to be the case. You're not always going to be dealing with data where you have this kind of intuitive idea of, whoa, I shouldn't use that. And so that's why we just kind of label it extrapolation. And then we're kind of proceed with caution. Maybe it is our best prediction, right? Sometimes we have to use it, but then we have to have a little asterisk that says this prediction is unreliable, right? Because it's not from our data, right? Or from the range of our x's. Just to kind of, if we use the regression line to summarize what we were just saying, to extrapolate, then the predicted value of y might still be our best prediction, but it's an unreliable prediction. So if we use the regression line to extrapolate the predicted value of y, it will be our best prediction. Right? If we have no other thing to go off of, it'll be our best prediction. But the prediction will be unreliable. Oops. So now that we are armed with extrapolation, I can continue these question parts in my mind. So from E to F, I feel like usually I go to J or something like that, which is a little bit aggravating, I know that. Part F. Oh, there's only 3 questions. Yeah, but they have parts like A through III. Crazy. But they're all pretty straightforward, right? And hopefully easy marks. If we were to predict the gift aid of a student whose family income is $100,000 per year, we can do that. So let's do it. Predict the gift aid of a student whose family income is, let's say, 100,000 per year. To make these predictions, right? We're going to use the line that we built, which is this one here. Copy. I want to predict the gift aid, and this is when it's really useful to kind of substitute the name of the variable into the formula. Of course, you could have y hat and just x, but sometimes it's nice when you're reading these prediction questions. So predict the gift aid of a student whose family income is 100,000 per year. Now we're just going to substitute in the 100,000. If we had manipulated the units, then you would need to do that, but we did not. 24,327.71647 minus 0.04311 times 100,000. Just kind of skipping straight to it. I get 20,016.71647, which in terms of dollar amounts have two decimal places, 20,016 and 72 pennies. How about part G? Now, spoiler alert, I'm going to make you extrapolate and make you say that this thing is not reliable or this prediction is not reliable. How am I going to do that? Well, here we go. Predict the gift aid of a student whose family income is, let's use that million, whose family income is 1 million per year. Oops. And then I prompt you with, do you trust this prediction? We still use the line. It's the only thing we have. So we can still do the prediction. I guess make the prediction or whatever the term would be. Plugging in a family income of 1 million, I get 24,327.71647 minus 0.04311 times $1 million. Does in fact land me at a negative predicted value, negative 18,782.28353. Maybe this is a good formula for how much you should be donating to your kids' college or whatever, besides tuition. I don't know, just making this stuff up. So then, okay, let's go to our scatter plot, which I should have done for the first one as well, right? But I know that an income of 100,000 is within the range. You can also use this kind of to double check that 20,000 that we predicted kind of makes sense, right? So before we used 100,000 and kind of predicted 20 something, it all checks out, makes sense. Right now, if I use 1 million, it's going to be way out here. So no, I do not trust this prediction because I'm extrapolating beyond the range of the data, would be my generic answer. Put it on a fresh page here. No, I do not trust this prediction. You have to tell me why though, right? Yes or no answers won't get you any marks, and that's a fact, right? You have to tell me why, because
It's treacherous.
it's so treacherous. Because we are extrapolating beyond the range of the data. Oops. right? And I'll just add in brackets here that 1 million in family income is not within the range of our X's. It's not within the range of our X's.
When we stop that,
Yeah. I'd love to see beyond the range of the data. It is redundant because the definition of extrapolating is that you're predicting beyond the range of the data. So yeah, you got me. I want to see extrapolating though, or something about it being beyond the range. But at that point in my marking, I'm usually pretty tired, so I'll let a lot of stuff slide. Especially if it's true. Well, yeah, you got me. You got me. All right. So, last thing we're going to talk about is R squared. R squared, you might have, when you've likely seen R squared before, it's a measure of how well our model fits the data, if it's a linear relationship, right? And so R squared is kind of the last thing I'm going to bring up here. And again, I'm going to use the definition of R squared and apply it to the question. So let's start with the general definition. R squared is the percentage of variability in Y that's explained by the least squares regression line on X. Now I know that that's a lot to absorb, right? So as soon as you see percentage of variability or proportion of variability, I want your brain to say R squared, right? And then just kind of confirm that that's it, right? But the percentage or proportion, right, depending on what you prefer, the percentage of variability in Y explained by the least squares regression line on X. Now, of course, you'd replace the X's and the Y's with the question specific variables. But like I said, as soon as you see percentage or proportion of variability, right, that's going to trigger you R squared. Okay. And what is R squared? We can calculate R squared is the correlation squared. So if you have correlation, which we do in this case, right, then I can square it and then I have my R squared. Now R squared, right, is either a percentage, then you'd have to multiply it by 100, or a proportion, you can leave it as is, right? But a high R squared, right, so close to 1 or 100%, just think about, so correlation goes from -1 to 1, right? When I square a negative value, it becomes positive, putting R squared between 0 and 1, and that's why it can be a percentage, right? And so a high R squared, a high value of R squared, which really just means close to 1 or 100%, is a reflection of a strong model, which means that we have these very reliable results, right? If our model is strong, then we can put a little bit more faith in our predictions. So is I'll say reflection of a strong model. Which means reliable predictions. I'll clean that up. So the final part of my made up question here is going to ask, and I'm going to try to keep it on. Where's this page break? Oh, I can do a line. I can afford a line here. Not so squished. So part H is going to say something like, what percentage of variability in gift aid is explained by the least squares regression line on family income, right? That's a very overwhelming question if you just take it for what it is, right? But as soon as you have that trigger of percentage of variability, then you know you need the R squared. So what percentage of variability in gift aid is explained by the least squares regression line on family income? Right, this could also be or proportion, but in this case, I'm asking for a percentage. Okay, so it could say proportion, but in general, right, we're going to see this and think R squared. Okay. All right. Luckily, I have the correlation, so R squared is R squared, which is negative 0.499 squared. Which puts me at 0.249001, or as a percentage, 24.9001%. Right, and just here's the proportion of variability, and here's the percentage. The other way that this question could have been set out in the beginning is I give you the scatter plot, and instead of the summary statistics, I only give you the two means and the two standard deviations and not the correlation. Okay. But then one of the first things I tell you is that, for example, 24.9% of the variability in gift aid is explained by the least squares regression line on family income. What is the correlation? Right? Then it's a little bit more work, right? Because R squared, once I take the square root of it, I'm still gonna have a positive number. So then I need to look at my scatter plot. If I have a negative relationship, I need to add that negative, right? But then that's how you would have the correlation. Okay. So that's just the two ways that these things can go. Okay. And that's good for today. I have nothing more to add, I don't think. If you have any questions, let me know, but I will stop this recording.